Welcome back. So, in this video we will look into the examples of reducing a linear partial differential equation of second order. We will try to reduce them into normal forms. So, the simplest examples that we consider first with equations with constant coefficients. So, linear second order partial differential equations with constant coefficients we consider, and with the process that we learned in the last few videos, we reduce this equation into canonical form or simpler form into new variables. So, in equation in new variables xi and eta, so that if that is simplified equation, if it is solvable, we will try to solve. Okay. So, that is what we will see. We will start with an example. So, reduce this, if an example of each example we do. So, for each case of hyperbolic, elliptic and partial parabolic, in each of these cases we will do an example. So, we will start with an example here. So, reduce the equation, reduce the PDE, that is partial differential equation, 4 times uxx plus 5 times uxy plus uyy plus ux plus uy equal to 2. So, this is the equation into a canonical form, into a normal form or a canonical form. So, what is the solution? Solution is we have to reduce this into form. So, what is that? So, just consider this is your A. So, A is 4, just observe that A is 4, B is 5, C is 1 and D, E is 1 1. So, that we do not really need. So, what you have to see is the discriminant. Discriminant is B square minus 4AC. Just look at B square minus 4AC. Its value is 25 minus 16. So, this is going to be 9. B square minus 4AC is 9. So, which is positive. So, that means what we learned is it is hyperbolic equation. Hyperbolic equation. So, equation is hyperbolic. Where is that domain? So, first of all you have to see the domain. So, it nothing is given, that means x y belongs to the plane. So, that is your domain of the differential equation, partial differential equation. So, in this you take any point, because B square minus 4AC is this is the coefficients are valid everywhere. Okay. So, this is a hyperbolic equation in the plane. So, this is your domain. So, for every x y in this domain, this equation is hyperbolic equation. So, that is clear. So, that is what you can conclude by looking at the discriminant. Now, how do I get my new variables? Or you consider dy by dx equal to b plus or minus, plus, first of all plus you choose 1, b square minus 4ac by 2a. This is 1 and you consider the other one, b minus square root of b square minus 4ac divided by 2a. So, this is what we have seen. If you consider, that is, if you make a star and c star equal to 0, okay, this is what you see, that you will see that if you look for this transformation from xy to xi eta, you see that these are the ODEs you have to solve that fixes your xi and eta. So, if you see this dy by dx, b is 5 plus square root of b square minus 4ac is 9. So, that is 3 divided by 8. So, you have 1, and in this case the other ODE becomes dy by dx equal to 5 minus 3 divided by 8. So, this means 5 minus 3, that is 2. So, 1 by 4. Okay. So, these are the two ODEs you have to solve. Dy by dx equal to 1, that will give you y minus x equal to constant C1. And what happens here? Dy 4 dy minus dx, 4 dy minus dx equal to 0. So, this you can directly integrate and to get right, or you simply dy equal to 1 by 4 dx. So, this you integrate both sides to get y equal to 1 by 4x plus C2. So, if you rewrite, this is like 4y, bring this minus x this side. So, you have this is equal to 2. So, these are the two equations, two solutions, general solutions of these two ODEs. So, this So, from this we have seen that xi of xy equal to y minus x, and eta of xy is 4y minus x. This is how you fix your xi and eta. Now, so what you have, so your equation is involving uxx, uy, uxy, uyy, ux, uy. So, you need to find ux and uy. So, just like dou x, dou u by dou x in terms of new variables. So, dou u by dou xi into dou xi by dou x plus dou u by dou eta into dou eta by dou x. So, this will give me dou xi by dou x, that is minus dou u by dou xi plus dou eta by dou x, again you have a minus dou u by dou eta. So, that is what is my dou u by dou x. And what happens, dou u by dou y, replace x by y. So, you have dou u by dou xi, dou u by dou x you have to replace with dou xi by dou y plus dou u by dou eta by dou y. So, this becomes dou u by dou y becomes dou xi by dou y is 1 again. So, you have dou xi by dou u by dou xi, and here plus dou eta by dou y is here 4 times dou u by dou eta. So, from this, so you already got what is u xi, uy, ux and uy, but you need uxx. So, look at this uxx. To get uxx, what you get is, if you want this, that is dou square u by dou x of u. So, if you apply this, what is dou x to get, simply you ignore. So, that is what is a minus dou xi plus dou eta is your dou x. One more time that, so that will give you minus plus dou u by dou xi plus dou u by dou eta. So, if you apply this you do it. So, you have u xi plus u xi eta plus u xi eta xi, they are continuous. So, you have 2 times, so u eta. That is all. Okay. So, this is what use your uxx, and from here you can also get uyy, or first of all you get uxy. Uxy is, one is minus dou x, this is like dou x dou y of u, or dou y dou x of u. So, this both ways you can take. So, dou x I replace with minus dou xi plus dou eta into dou u by dou y, you simply write dou whatever you have here, dou u by dou xi plus 4 times dou u by dou eta. So, what is this one? So, this will give me uxy as minus u xi, and you have minus u xi eta, and here plus 4 u xi eta. So, that will become plus 3 u xi eta. Xi eta, u xi eta or u eta xi, both are continuous. You assume that the second derivatives or mixed derivatives are continuous. Okay. If u xi eta, those mixed derivatives are continuous, then it should be same. So, that is from the calculus. Okay. And then finally you get 4 times u eta. So, because you are working here with for the equation that is with constant coefficients, that is why it looks easier. You see this when you are expanding. So, you have to be careful if these coefficients are functions of x, y. Okay. So, you have to carefully expand it, otherwise you may go wrong. So, this is what is your uxy. So, same way you can get uyy. Uyy is simply dou xi plus 4 dou eta, that is my dou y from here. Okay, and then dou u by dou y, you write again dou u by dou xi plus 4 times dou u by dou eta. So, this becomes uyy becomes u xi, this mixed derivative plus this mixed derivative, this one and this one. So, together will give me 8 u xi eta plus 16 u eta eta. It is just like a plus b whole square type. Okay. So if you do this, you can easily see u xi square. So xi eta u xy. So you have 2 times 4. Okay, 2 4 8 and 4 square. Finally 4 square eta eta. So this is how we get. Okay. So now you know all these uxx, uyy and uxy, ux and uy in terms of xi and eta only. So just put it into the equation. So what is the equation? 4 times. Now your equation is 4 times ux. Ux is 4u xi plus 2u xi eta plus 4 u eta eta. This is what is my uxx. Next is 5 times u mixed derivative, that is u xi minus u xi. Then I think I made a mistake, so it should be minus 4, right. So this is plus and this is everywhere I think minus. Okay. So mixed derivative, so I have a minus and you have u xi and this is also 4, that is going to be actually 5 minus 5. 4 u xi eta and 4 u xi eta if you apply to this here, and if you apply eta here, so you get 1, so total 5, so you have this one. So that is the correct. Now this is all with minus. Okay. Then finally, so you see that u xi minus 5 u xi eta minus 4 u eta eta plus uyy. Uyy is u xi plus 8 u xi eta plus 16 u eta eta plus ux. Ux is simply u xi plus u eta. That is what you have, u xi. So you have minus, so that is minus. Okay, minus u xi minus u eta. That is ux plus uy. Uy is u xi plus 4 eta equal to 2. So this is what, if you substitute, this is what it becomes. So now collect the terms, u xi terms. 4 plus this is u, right. So 4 u xi, 5 u xi. So I have minus 5. This cancel. So you have got gone. So similarly 4 eta eta, 16 eta etas, 20, and here minus 20. So you have, this is gone. So what you are left with is only 8 u xi eta and you have a minus 25. 8 minus 25 is minus 17. 17 u xi eta and you have plus 8 u xi eta. So that is minus 9. So together minus 9 u xi eta, and here also you get u xi goes, and this becomes plus 3 u eta equal to 2. So this gives me u xi eta minus 1 by 3 u eta equal to 2 by 9. So this is what is the equation now. Okay. So this is mixed derivative, so that means hyperbolic, you can easily see. So how can we solve this equation after reduction? That may be tricky, we do not know. So we can solve it, actually we can solve it. How do we solve it? This is a partial differential equation. I am just giving you the method to solve this one, just using basic methods of ordinary differential equations. So if by considering, this is what is the canonical form. I reduce this given partial differential equation of second order into another partial differential equation of second order, but in the canonical form, nice form, simpler form. This is called normal form or canonical form. So this we can solve now using the techniques that we learned for ordinary differential equations. So if you consider this u eta as some v, okay, v, you just take it. So then what happens to this equation? So you have dou v by dou xi minus 1 by 3 v equal to 2 by 9. Okay. This is a ordinary differential equation type. Okay. So, how do I solve this? So what is the integrating factor? So, assume that it looks like first order ordinary differential equation, linear ODE, first order linear ODE. So, e power, if I multiply e power integral integral p is minus 1 by 3 d xi. Okay. So, this is my integrating factor. Integrating factor is this. So, you have e power minus xi by 3 plus, now this is a PDE. So, there is the integrating factor, right. So, this is the integrating factor, and any constant into that is also a integrating factor. Here we are dealing with the partial differential equation. So, this constant, if it is an ordinary differential equation, this is a constant, any constant times is fine, but here C can be any function of eta. So, you can choose C times some eta, C of eta into this acts as integrating factor. So, you substitute, you multiply that C power e power minus xi by 3 into C xi, C eta into dou v by dou xi minus 1 by 3 e power minus xi by 3 v into C of eta equal to 2 by 9 C of eta e power minus xi by 3. That is what I multiplied both sides. If you do that, so what is this one? This is actually equal to this becomes this is dou xi of e power minus xi by 3 into v equal to 2 by 9 e power minus xi by 3. Okay. So, you need not consider this. Okay. So, finally it's not it's cancelling both sides. So, this is what is, so integrating factors can be anything, but just for the sake of completeness, it is not constant, any constant, this constant is actually C of eta. You can choose as a C of function of eta, because it is a partial differential equation. We are using the methods of ODEs. So, if it is possible we can solve. So, this is what you get, this is the equation. Now, you can integrate both sides. So, if you integrate with respect to d xi, so what is the integration constant? That can be any function of eta. So, that I am calling C1 of eta. Okay. If you differentiate now, you get back what you want, this one. Okay. So, this will give me e power minus xi by 3 into v of xi eta. Okay. So, this is a v is unknown function. So, this is equal to, so this is 2 by 9 comes out, e power minus 1 by 3 is minus e power minus xi by 3. So, minus 6 by 9, that is 2 by 3. So, this is what, if you differentiate this, you will get this integrand. So, this is plus C1 of eta. So, this implies a v of x, v of xi and eta is actually, now you take this minus 2 by 3, if you bring it, plus C1 of eta into e power xi by 3. So, this is what I found as a function of as a v. What is v? V is u eta. So, u of xi eta. So, that is u eta equal to minus 2 by 3 plus C1 eta into e power xi by 3. But this is a, but this may not be, you may not be able to integrate. This is like dou u by dou eta. So, this is what is the equation now. So, if you want to get u xi eta, so you have to integrate this equation. Can we integrate this? Actually you can, right. So, you simply integrate both sides with respect to dou eta d eta. So, you integral of this whole thing with d eta. Now, because you are integrating with respect to eta, any some new function, that is the integration constant, that is xi. So, this will give me u of xi eta finally equal to minus 2 by 3 into eta plus integral. So, this is a constant, it is nothing to do with eta. So, you have e power xi by 3 comes out, integral C1 of eta d eta, that integration whatever any arbitrary constant, that integration plus C2 of xi. So, this is what is your general solution of the partial differential equation. Okay. This is the general solution of the PDE of the PDE of the standard form, of the normal form, of the normal form, canonical form or normal form of given PDE. Okay. So, why I am calling so general solution again. So, in ordinary differential equations, second order equation, when you integrate, the general solution should involve two arbitrary constants. So, we call in the partial differential equation, we call the general solution if it involves two arbitrary functions. Okay. So, that is what you have here. So, u xi eta is actually C1 of eta, that is one arbitrary function, and C2 of xi, that is another arbitrary function. So, you have two arbitrary functions here. So, that is why I am calling it general solution, like same way we have done for ordinary differential equations. So, this is the general solution. Like this you can solve given equation, you reduce this into standard form. If possible, it can be solved. If it is after reduction, if it is in a simpler form, then it can be solved. It can be solved for its general solution. So, this is the solution for the reduction equation. Now, to get back my new variables for actual partial differential equation, you can also simply replace x, xi, y, xi and eta as your functions. Xi and eta are y minus x and y minus 4y minus x. Okay. So, that you can replace and it becomes function of, this is a function of u of xi eta becomes u of function of x y, this becomes minus 2 by 3, eta is 4y minus x plus eta x y minus x by 3 and integral C1 of 4y minus x. So, this is nothing. So, this is eta d eta. So, eta. So, whatever the variable. So, if you replace, so you can say that is 4y minus x and d eta is d of 4y minus x. Okay. If you write, you can plus C2 of y minus x, xi is that. So, this is a function of general solution of a given partial differential equation. Okay. This is the general solution of given PDE, because this also involves, this is arbitrary function and this is also arbitrary function. So, this is your function, everything is in terms of old variables, this x and y. Okay. So, this is the form, you give any C1 and C2 and this actually solves the given differential equation. Okay. So, you choose any function C1 and C2, whatever may be function, it will satisfy the given partial differential equation. So, this is how we solve. We can first reduce this given partial differential equation into standard form and then see the normal form, reduced normal form, if it can be solvable. If it is in a simpler form, try to integrate directly. So, only simpler methods are simply integration. Okay. You do not know any method how to solve a partial differential equation. So, if you can only integrate those methods, elementary methods, you can apply and get your general solution. Now, we will see the other example where you see different other type of equations. We will consider one more example. So, consider this uxx. So, equation is uxx plus uxy plus uyy plus ux equal to 0, reduce into canonical form, reduce the equation, reduce the PDE into normal form. So how do we solve? Again we see, look at A, B, C. A is 1, B is 1 and C is 1. So B square minus 4AC value is 1 minus 4, that is minus 3. So this is negative. Immediately you can say that A equation that is valid in the full plane is elliptic equation. So equation is elliptic, I can directly conclude by just looking at the discriminant B square minus 4AC. Now you consider your xi and eta from this by solving these ODEs. B is 1 plus square root of B square minus 4AC, that is 3i, root 3i, okay. So divide by 2a, so that is 2, and also other equation is dy by dx which is equal to b minus square root of B square minus 4AC, that is minus I root 3 divided by 2. So these are the two ODEs. So you have to solve. So if you do this, if you try to solve this partial differential equations, so by solving these ODEs, you can see that your xi of xy will be whatever is the solution. So solution is, or you simply solve it first. So y is, this is dy equal to 1 plus or minus 1 by 2 plus I root 3 by 2 times dx. So this becomes y minus 1 by 2 plus I root 3 by 2 into x equal to C1. So this should be your xi of xy. And similarly here, because these are complex things, so you can see that if you directly do dy equal to minus dy equal to half minus I root 3 by 2 dx. So you get y minus 1 by 2 minus I root 3 by 2 dx equal to C2. So this is what you get, this is your eta. So you can see that xi equal to xi bar is actually eta, okay. So eta is nothing but xi bar, that is what you can easily see. So this is your xi bar. If this is your xi bar is simply eta. So when I have this one, so I know that if you actually reduce, if you now try to look for uxx, uxy and uyy and ux in terms of these new xi, these variables xi and eta, you know that it will become u xi eta plus lower order terms equal to 0. That is what it will become, okay. This is the canonical form you will get, you can expect. Canonical form you can expect, but then these are complex valued functions. So there is no meaning. So partial derivatives with respect to a complex valued functions, variables are complex, there is no meaning, okay. So what we do is, we do not do this in between intermediate step of finding the canonical form. So immediately once you see that the complex, you take the real part. So alpha is a real part, xi plus eta by 2, that is simply y. Beta is, these are the variables you look for, okay, instead of xi and eta. Beta is so xi minus eta divided by 2i, that is simply minus so here it will be y minus, so real part y minus xi minus eta by 2, xi plus eta by 2 will be xi minus x by 2, y minus x by 2. Beta will be simply root 3 minus root 3 by 2 x, okay. So this is what you see plus actually. So I times minus, so it does not matter. So this is what you have. So if from xi, if you take alpha beta as a real part of xi, this is what you get, imaginary part of xi you take, and this is what you get, okay. or you can also choose real part of eta, that is same, this is your alpha, real part of eta if you choose here, this is going to be plus, you can choose any one of them. So these are the new variables if you look for, then you try to see what is your ux. Ux is dou u by dou alpha by dou x plus dou u by dou beta by dou x. So this is what in terms of xi, not in terms of xi and eta, when they are complex functions, you choose only real and imaginary parts of the each any xi and eta, okay. Then you can choose these new variables as alpha and beta. So in terms of this alpha beta, you expect this canonical form become u alpha alpha plus u beta beta plus lower order terms, that is what we will get it. So ux is this, so that is, so u alpha by a is a minus half u alpha, and dou beta by dou x is root 3 by 2 u beta. So you can choose simply for xi, so that you have minus minus, that is going to be plus, okay. So maybe you can expect calculations will be simpler if you choose maybe minus root 3 by 2, because you see minus both places, so I can take it out. So you can choose, okay. I have chosen alpha beta as real and imaginary parts of xi. You can also choose real and imaginary parts of eta, there is no issue, okay. So you can choose. So this is what is my ux. Uy is the same thing, dou u by dou alpha, so that is u alpha into dou alpha by dou y, instead of dou alpha by dou x, you have dou alpha by dou y, that is simply 1. So you have u alpha and plus dou beta by dou y, that is there is no function of y for beta, so that is 0. So I have simply dou u by dou y is simpler form. So that is it. So you have uxx is minus of dou alpha plus root 3 by 2 dou beta into minus minus plus again, so half u alpha plus root 3 by 2 u beta. So this is simply 1 by 4 u alpha alpha plus, so what is this one, 2ab, so that is root 3 by 4, 2 root 3 by 4, that is root 3 by 2 u alpha beta plus 3 by 4 u beta beta. So this was my uxx. Uxy, so uxy also you can calculate, that is dou x of dou u by dou y. So I know what is my dou u by dou y, that is dou x you can replace from here. So from this minus half dou alpha plus root 3 by 2 dou beta is my dou x. This is my dou x. So this into dou u by dou y is u alpha. So that everything in terms of alpha. So you have 1 by 2 u alpha alpha minus root 3 by 2 u alpha beta. And what happens from here, you can get uyy also. Uyy is simply u alpha alpha. What is this? How do you get this? Dou y of dou u by dou y. What is dou y is dou alpha. Dou alpha of dou u by dou y is u alpha, that is u alpha alpha. So you have got everything, uxx, uxy, okay, uxx, uxy and uyy. So and ux, uy are already here. So if you substitute into the equation, then you get the canonical form that may be either solvable or not depending on its simplicity. So you have uxx, that is 1 by 4 u alpha alpha plus root 3 by 2 u alpha beta plus 3 by 4 u beta beta plus uxy, that is minus 1 by 2 u alpha alpha minus root 3 by 2 u alpha beta. Now plus uyy, that is u alpha alpha, okay, plus ux. Ux is, what is ux is half u alpha, and you actually have minus root 3 by 2 u beta equal to 0. So this is what is your equation. So this is your ux, uyy, and this is your uxy, and this is your Uxx. So, your equation becomes PDE becomes given PDE becomes this one. So, this implies now you can simplify and you see that 1 by 4 minus half. So, this is going to be, so this is 2 by 4. So, you have minus 1 by 4 u alpha alpha. So, that is what is u alpha alpha terms and plus 1. So, plus 1 if you say, so you have plus 1 is 3 by 4 together. So, 1 minus 1 by 4 is 3 by 4. So, 3 by 4 u alpha alpha, and what happens to u alpha beta? This one and this one, that is all. So, this gets cancelled, and u beta beta I have only this one. So, you have again 3 by 4 u beta beta, and now this also gone, right. So, we have considered this, and what you are left with is minus 1 by 2 u alpha minus root 3 by 2 u beta equal to 0. So, this is your canonical form. So, that is u alpha alpha plus u beta beta equal to 4 by 3, that is 2 by 4 by 3 into half 2 by 3 u alpha plus, take it to the other side, 4 by 3 2 root 3 by 3. Okay. So, that is going to be 2 by root 3 into u beta. So, this is what the equation becomes. This is the canonical form. This is the elliptic canonical form. Okay. So, that is what exactly we have seen. So, u xi eta is canonical form in terms of these new variables alpha beta, and that becomes if you actually do 2 times, this is what you will get. Instead, you can directly get into the, you can directly write in terms of x y. Okay. So, you choose an alpha beta as a real and imaginary part of xi and eta. So, you have not done, you have not made 2 steps like we have done for the general equation. Get the canonical form, reduce the equation in terms of xi and eta, where xi and eta are complex valued functions, and then choose new variables alpha beta, and then reduce that equation into in turn again one more form like this. So, instead you can avoid that intermediate step, directly choose the variables, because you know xi and eta, you take the real part, imaginary part as alpha beta, it will become this canonical form. This is the elliptic equation, but you cannot expect this to be solved like earlier case, because you cannot integrate. This is not easy. Okay. This is a partial differential equation which you do not know still. You cannot use any ordinary differential equation method to solve this elliptic equation. So, this is how you can reduce second order partial differential equation into a canonical form. So, we have seen 2 examples, one for hyperbolic, one for elliptic. So, in the next video we will try to find canonical form of a linear second order partial differential equation. We will try to reduce that equation. We will first see, we will try to take partial parabolic type of equation, just looking at its discriminant. If the discriminant is 0 for a given PDE, then it is a parabolic. So, for such an equation we will reduce by choosing. If you have to choose properly, you will only get one variable, either xi or eta. So, you have to choose the other variable in such a way that a Jacobian should not be 0. So, we will see that example in the next video. Thank you very much.